Dissolving sugar into a glass of water seems straightforward until the grains simply stop disappearing and settle at the bottom. This physical limit is solubility, the absolute maximum amount of solute a solvent can hold at a specific temperature. Whether that solute actually dissolves depends on the like dissolves like rule. Polar solutes easily mix into polar solvents, like salt into water. But if you drop a non-polar solute like naphthalene into that same water, the molecules reject each other. Solubility isn't achieved through aggressive stirring. It is governed by the compatibility of intermolecular forces. If those forces do not match, the substances will remain separate. When a solid is added to a liquid, two processes begin simultaneously. Particles break away to enter the liquid during dissolution, while others collide with the solid surface and reattach during crystallization. Eventually, the system reaches a state where the rate of particles entering the solution exactly equals the rate of those leaving it. This is dynamic equilibrium. A saturated solution is the physical result of this balance. At this stage, no additional solute can be absorbed by the solvent. Even though the solution looks stable to the naked eye, it is in a state of continuous, high-speed exchange between the solid and liquid phases. Unlike solids and liquids, gases are highly compressible. This means their ability to dissolve in a liquid is almost entirely dependent on the pressure applied to the system. This relationship is defined by Henry's law, which states that the solubility of a gas is directly proportional to its partial pressure. This is expressed as P equals kH times X, where P is the partial pressure, X is the mole fraction of the dissolved gas, and kH is the Henry's law constant. While solids often require heat to increase solubility, more gas can be forced into a liquid simply by increasing the ambient pressure. The value of kH is specific to each distinct gas, and it rapidly changes based on the temperature of the surrounding environment. On a graph of partial pressure versus mole fraction, the slope of the resulting line is kH. Because kH represents the pressure required per unit of solubility, a higher constant value indicates that the gas is less soluble. As temperature rises, kH increases, and gas solubility drops. This is why aquatic life is more comfortable in cold water. The lower constant allows for higher concentrations of dissolved oxygen than in warm water. Whether through high temperatures or high kH values, these physical factors limit the amount of gas a liquid can hold, affecting everything from detailed lab calculations to global environmental health. Soft drink production uses this mechanic by sealing carbon dioxide into bottles under extreme pressure. Once the cap is removed, the pressure falls and the gas instantly escapes as bubbles. Scuba divers experience this when breathing compressed air at great depths. The high pressure forces nitrogen into their blood. If they surface too quickly, the nitrogen comes out of solution and forms bubbles in the bloodstream, causing decompression sickness. By controlling pressure, we can manipulate the concentration of dissolved gases for both industrial manufacturing and human safety. Let's apply this to a specific problem. If we have a partial pressure of 0.987 bar and a kH of 76.48 kilobar, we can determine the dissolved quantity. First, we must convert the kilobars to bars to ensure the units match. Dividing the pressure by the constant gives us a mole fraction of 1.29 times 10 to the negative fifth. To find the amount of gas in a 1 liter volume, we must account for the moles of the solvent itself. 1 liter of water contains exactly 55.5 moles. Multiplying the mole fraction by 55.5 results in the final quantity, 0.716 millimoles of dissolved nitrogen. Solving these problems requires combining the direct proportionality of Henry's law with the molar constants of the solvent to reach the final dissolved amount.